Have you ever just stood there looking at something like the Grand Canyon or maybe a super rugged coastline and just thought, how in the world did this get here? Well, today we are pulling back the curtain on the two powerful, relentless forces that are constantly sculpting our planet, weathering and erosion. So let's dig in. I mean, it's a huge question, right? You see these unbelievable landscapes, and you can't help but wonder how they were formed. The thing is, it's not a single event. It's this incredibly slow, powerful, and constant process. And today, we're going to get into the secrets behind nature's incredible artistry. Okay, so to really get this, we need to meet the two main characters in our story, weathering and erosion. The easiest way to think about them is as a team. Weathering is the breaker. Its whole job is to smash, crack, and dissolve rock right where it sits. Then erosion comes along, it's the taker. It picks up all those broken pieces and just carries them away. One breaks, the other takes. That is the fundamental difference right there.
So let's take a closer look at these two sculptors and give them their official definitions.
First up, weathering. Now, the most important part of this definition is the phrase without moving them. This is always step one. It's all about weakening and breaking down the rock on site, turning big, solid rock into smaller rocks, pebbles, and eventually sand and soil.
And that's when erosion takes over. Once weathering has done the hard work of breaking everything down, erosion is basically the transportation system. You've got these powerful forces, rivers, glaciers, wind, acting like nature's own conveyor belts, just moving all that material somewhere totally new.
Okay, so how does weathering actually break rocks apart? It's not just one thing. Turns out, nature has a whole toolkit for this job. So we can pretty much sort all of weathering's tricks into three main categories. You've got mechanical weathering, which is all about physical force. Then there's biological, which is when living things get involved. And finally, chemical, which, well, it actually changes the rock's chemical makeup. For today, we're going to focus in on the first two. Let's start with mechanical weathering. This is pure brute force. It's all about physically shattering a rock without changing what it's made of. Think of it like dropping a plate. You end up with a bunch of smaller pieces, but it's all still the same ceramic.
And this right here is a perfect analogy. Imagine a rock that formed way deep underground, under an insane amount of pressure. When geological forces push that rock up to the surface, all that pressure is suddenly gone. So the rock expands and literally cracks apart, just like a frozen glass that shatters when you hit it with hot water. It's this massive release of built-up tension.
Another huge player in mechanical weathering is something called frost wedging. It's a slow process, but it is incredibly powerful. First, a little bit of water gets into a tiny crack in a rock. Then it freezes. Now, when water freezes, it expands by about 9%, and that expansion forces the crack to get just a little wider. The ice melts, more water gets in, it freezes again, and this cycle just repeats over and over until a massive boulder can be split clean in two. And if you want to see this in action, you don't have to go far. This exact same process is the reason we get potholes in the road after a cold winter. It's a perfect, everyday example of geology at work right under our feet or under our tires. Then you have biological weathering. This is where life itself becomes a destructive force. I'm talking about a tree root slowly but surely growing into a crack and prying a rock apart. Or think about animals that burrow into the ground, or even little clams that bore right into solid rock to make a home. So we've seen how weathering breaks rocks down, but that's just half the story, right? Now we need erosion to come in and haul all those broken pieces away. And we're going to start with one of the most powerful agents of erosion on the planet, flowing water. This seems like a simple question, doesn't it? You look at a river, you see water moving, but is all of that water moving at the same speed?
You might think so, but the answer, surprisingly, is a big no. A river's speed is actually pretty complex, and it all boils down to one simple concept: friction.
So yeah, the reason is friction. Anywhere the moving water touches something that isn't moving, it slows down. This happens along the bottom of the riverbed, along the banks on both sides, and even at the very top where the water's surface meets the air. What that means is the fastest water is usually right in the middle of the channel, just a little bit below the surface. Now, because a river's speed isn't the same everywhere, it carries all that broken down rock, what we call sediment, in different ways. The tiniest particles are actually dissolved right into the water. That's the dissolved load. Lighter stuff like silt and clay gets carried along in the flow. We call that the suspended load.
And then, the heavy stuff, the pebbles and rocks, they just get rolled and bounced along the bottom. That's the bed load.
And here is the key takeaway for rivers. Velocity is everything. Fast-moving water has a ton of energy. It can pick up bigger, heavier rocks and tear away at the riverbanks. But the second that water slows down, it loses energy, and it has to drop whatever it's carrying. That's how you get sandbars and deltas. This constant dance between speed and sediment is what carves out entire valleys over millions of years.
But water is not the only heavy hitter when it comes to erosion. Let's talk about something way bigger and a whole lot slower: glaciers. These things are truly nature's bulldozers.
Glaciers are just unbelievably powerful, and they erode the land in two main ways. The first is called plucking. So meltwater from the glacier seeps into cracks in the bedrock below. When that water refreezes, it acts like glue, locking the rock to the bottom of the glacier. As the glacier inches forward, it literally plucks that rock right out of the ground. The second method is abrasion. All those rocks that got plucked are now stuck in the ice at the bottom, turning the glacier into giant sandpaper. As it moves, those rocks scrape and grind away at the ground, leaving behind these long scratches you can still see today.
So when you put it all together, the breaking and the taking, the flowing water and the grinding ice, you start to realize that the surface of our planet is anything but permanent. It's constantly in motion.
And this is really the bottom line. Weathering and erosion are locked together in this continuous, planet-shaping dance. Weathering breaks down mountains, providing the raw materials, and erosion acts as the delivery service, carrying those materials away to build brand new landscapes, like fertile valleys, huge deltas, and sandy coastlines. It's a never-ending cycle of destruction and creation. And that leaves us with a really fascinating thought to end on. These processes have been happening for billions of years, and they're not stopping anytime soon. So if we could hit fast forward, say 1,000,000 years into the future, what would the Earth even look like? What new canyons or coastlines would exist? It's just a powerful reminder that the world we see around us today is just one snapshot in a very, very long and dynamic story.